Say you're hiking on a beautiful summer day in Flagstaff, and you come across a nice-sized boulder that's just begging you to lift it up, just to see if you can do it. You're a very capable human, and you manage to lift it high above your head. The boulder calls to you again, enticing you to see what would happen if you dropped it to the ground from that height. You do. It drops to the ground with a thud and makes a clear indentation in the soil where it lands. Where did the energy come from to make the rock hit the ground as hard as it did? We know the answer to this question already from last lecture. The gravitational force, the weight of the boulder, did work on the boulder as it fell to the ground, and the boulder's kinetic energy increased by an amount equal to the work done on it. I'm going to offer another way of thinking about this event that has proven to be quite useful. This is the concept of potential energy, the energy associated with the boulder's position instead of its motion. Together, kinetic energy and potential energy make up the total mechanical energy of a system. The name potential energy is aptly chosen because it indicates that there is some potential or possibility for work to be done because of an object's position. In the case of the boulder, we lifted it up off the ground and thereby created the potential for work to be done on it by the gravitational force attracting it back down to the ground. The higher we lift it, the more available displacement there is for it to fall through, and thereby the higher the work to be done, potentially, if you let it go. For this reason, it's useful to think of there being potential energy stored in the system when it's high off the ground. When the boulder is completely still, but high off the ground, we say there is a lot of potential energy associated with its position, and no kinetic energy. When we let go of the boulder, we say that the potential energy is converted into kinetic energy as it gains speed and loses height. When it's the gravitational force that's the would-be actor on the object, we call the potential energy the gravitational potential energy. Gravitational potential energy is not the only type of potential energy, but we'll start there. Notice that this new way to think of the situation, there being potential energy based on its position, doesn't invalidate what we learned last lecture at all with work and kinetic energy. It just offers an additional way to analyze what's going on. Many times it will make your life easier to go with this potential energy approach over the other. So, if kinetic energy is equal to the work it took to get an object going by applying a force through a distance, then potential energy is simply the potential to get an object going because of a potential force acting through a potential distance. It's a little less abstract than it sounds. So let's derive the expression for gravitational potential energy, and you can see for yourself. So, we have our boulder that's falling to the ground, and let's say it starts at position y1. So let me amend this diagram I've just drawn up here. All right. So we're going to define here as 0 because that's the ground. Oftentimes we would define where an object starts moving at y equals 0, put our origin at the start of the motion. Sometimes that's useful, but for this approach, when we're talking about gravitational potential energy, we want to put it at the ground. So the origin is going to be here. And so this height that the boulder is at is going to be equal to y1. So this distance here is y1. And then the height that it's going to fall down to, let's say that it's going to fall down to here. That's going to be equal to y2. y2. And so this distance here, the actual displacement, the distance that it falls, is y2 minus y1, right? And of course, what's working on it is weight, right? That's why it's falling. So, given this, we want to find the work that would be done by the weight if the object were to be allowed to fall the potential energy. The weight and the displacement are in the same direction, so the work, which we're gonna call W sub grav, so the gravitational work, is positive. And so it's given by, right, it's always a force through a distance so the force is the weight, and we have y1 minus y2 mg y1 minus mg y2. You might think I made a mistake by writing y1 minus y2. It's actually because we're using y to denote height, which increases in the opposite direction that gravity acts. So it doesn't matter where you define your origin to be necessarily. That won't really affect the physics. The only thing is you must stick to y is increasing in the up direction and gravity acts in the down direction. Right? So then, just like we defined kinetic energy to be 1/2 mv squared, when we had a difference of things, we had a difference of two quantities set equal to work, we're going to define the potential energy to be this quantity mgy. So we have a difference of two quantities here set equal to work. Right? So that's the pattern, and it's going to recur over and over here. So that means that we are defining the potential energy, which is going to be gravitational potential energy, mgy. And just like we did when we derived the work energy theorem, we're going to say that the work done is equal to the difference in this potential energy, the difference in energies. U grav 1 minus U grav 2, or the inverse of U grav 2 minus U grav 1, which is the negative of delta U grav. All right. Box that into 2. So again, it's U grav 1 minus U grav 2 because of the way we've defined the y-axis increasing in the upwards direction and gravity acting in the downwards direction. And so the negative sign here is essential. All right. So let's talk about conservation of mechanical energy. So now we get to see what this potential energy can do for us and how powerful all this energy stuff is. So say we have a block that's only being acted on by its weight, just like the boulder. It can be moving up or down, it doesn't matter. It has some speed at speed v1 at point v1 and speed v2 at point v2. The work energy theorem tells us that the work done on the block equals the change in its kinetic energy. Right? This is a work energy theorem. This is the total work. The change in its kinetic energy. 2 minus K1. So with our concept of gravitational potential energy, we can say that the total work is also equal to the change potential energy. Oops. And we have it from there. So we can equate the two expressions that we have for work. There are two separate expressions we have here. One here and one there. We can set them equal to each other and get that delta K is equal to negative delta U grav, which is K2 minus K1 equal to U grav 1 minus U grav 2. And we can rewrite that as K1 plus, what did I do? Yeah, K1 plus U grav 1 equals K2 plus U grav 2. So the ones refer to some initial scenario or moment, and the 2 refers to a later scenario or moment, right? So when the boulder is up high, and then when it is dropped down, so this would be like moment 1, and then the boulder is down here, and we have moment 2. So it has kinetic energy and potential energy at this position here, and it has kinetic energy and potential energy at this position here. And so what this tells us, which is very important, is that the combined kinetic and potential energies at each of those positions are equal. Whatever total kinetic plus potential energy it had here, it's the same total energy down here. It just may have traded between kinetic and potential a little bit. So if we write these out, we have 1/2 mv1 squared plus mgy1, right? This is the expression for kinetic and potential, equals 1/2 mv2 squared plus mgy2. Just writing it out. So what this means is the sum of kinetic and potential energy is called the total mechanical energy of the system. And we often say that the total mechanical energy of the system is equal to E. So E1 is the mechanical energy at position Y1, and E2 is the total mechanical energy at position Y2. If gravity is the only force acting on the object, then E is constant. We say that the total mechanical energy of the system is conserved. This is the case because we have only conservative forces, i.e. gravity, acting on our object. There are both conservative and non-conservative forces, so this isn't always true, but gravity, among others, is a conservative force, so this conservation of total mechanical energy is true when gravity is the only force acting on the object. So this might seem pretty limiting, but if you remember, this was the case for all of our projectile problems. Gravity was the only thing acting on them. Okay, so let's do a quick example here. So here we go. Alright. A crate of mass m starts from rest at the top of a frictionless ramp inclined at an angle alpha above the horizontal. Find its speed at the bottom of the ramp, a distance d from where it started. Do this in two ways. A, take the level at which the potential energy is 0 to be at the bottom of the ramp with y positive upwards, and take the 0 level for the potential energy to be at the top of the ramp with y positive upwards. And then we'll address C afterwards. So on both of them, y positive is upwards, but we're changing where the 0 is defined. All right. So find its speed in two ways. So we're looking for speed. All right. So we have a ramp. We have some crate of mass m. Starts from rest at the top of a frictionless, the top. It's frictionless, it's at an angle alpha, right? We have y being defined as positive in the upwards direction. Okay. And let's see. So then there's a distance d, all right? So then distance d, the bottom of the ramp. This is d. Okay. So on A, we take the level at which the potential energy is 0 to be at the bottom of the ramp. So this is going to be where we define y equals 0 for A. I'll say A. And then for B, it's going to be at the top of the ramp. So B, just to get a little slightly ahead of ourselves, this is x, b. All right. So let's see, what is y1 and what is y2? Because what we know is we're going to want to apply our work energy, our energy stuff. So K1 plus U1 is equal to K2 plus U2. It's an energy analysis that we're doing. So in order to find out the potential energy, you're going to have values for y because it's mgy, right? So what are our y values in the diagram here? So for A, y2 is 0. y2 is 0, and for y1, we have it at this distance above. What is that distance? That distance, since we have the angle and we have the hypotenuse, that distance is d sine alpha. Right, d sine alpha. So d sine alpha is y1. So the only force acting on it is gravity. So the total mechanical energy is conserved. And we can go ahead and use this formula that I've already written down. And so let's fill it out. So we have 1/2 mv1 squared plus mgy1 is equal to 1/2 mv2 squared plus mgy2. So before we go plugging everything in, we want to solve symbolically, and before we even do that, we want to cross out the zero terms. So at the start, it starts from rest. The problem says starts from rest. Starts from rest. So that means that the kinetic energy is 0 to start. The potential energy is all of its energy. And it does have speed at the bottom because it's fallen down, it's gone down the ramp. But the potential energy, by the time it reaches the bottom of the ramp, that's where we define 0 to be. So the potential energy at the bottom will be 0. So we can pretty quickly cross out those terms. And all we're left with is the 2 that are left. So mgy1 is equal to 1/2 mv2 squared. That's what we're left with. And we're solving for v2. So if you solve for v2 from that, you get 2gy1, which is equal to, if you plug in what y1 is, d sine alpha, 2g d sine alpha. There it is. Of course, we don't have numbers. It's kind of an abstract, just symbolic problem, but that was a pretty easy thing to come up with from a fairly complex problem. All right, so now part B was to do it so that our axes were defined differently. Part B was to take the 0 level for potential energy to be at the top of the ramp. So that means, all that means for us is that for B, y1 is going to be different, and y2 is going to be different. So coming back to our diagram here, this is y1, and this is y2, right? And so y1 for B is going to be 0. And y2 for B is going to be negative. Negative, and it's that distance, d sine alpha. D sine alpha. Okay, so now we basically just do the same thing. We're going to apply our k1 plus u1 equals k2 plus u2. The same stuff applies. There's no kinetic energy at the start, and there's no potential energy at the end. So we have mgy1 is equal to 1/2 mv2 squared. And so then we solve for v2 again. And v2 is equal to square root of negative 2gy2 no. So the difference in assigning of our axes mattered for what we cross out here. So where we have defined 0, let's see, at y1, kinetic energy is 0, and potential energy is 0 because the potential energy is defined based on position. And so if y1 is 0, then you're plugging in 0 for mgy1. And so that's why, my mistake. And then these two are left. So then we have 0 is equal to 1/2 mv2 squared plus mgy2. We're solving for v2. B2 is equal to square root of negative 2gy2, which is just dandy because that negative is going to cancel out the negative we have up there. So, which is equal to square root of 2g d sine alpha. And of course we get the same answer because it doesn't matter how you define where your origin is, it just matters that the y is increasing in the upwards direction and gravity acts in the downwards direction. So part C, we'll get too ahead of ourselves, part C asks us about the normal force. So the normal force, let me pull the question right up here again. Why did the normal force not enter into your solution? So if we were doing this with Newton's tools, we would have had to analyze forces, we would have had to account for the normal force, and there's some weird angle going on, we would have had to take all kinds of components instead of the one quick one we did. But because we're analyzing energy and work, the normal force does no work because the direction that the box is traveling is this direction, and the normal force is acting in this direction, which is perpendicular. So the normal force doesn't contribute one bit to the work that's done. And so it doesn't come into our energy analysis at all. So this is a nice example of how energy analysis greatly simplified the problem that otherwise would have been pretty difficult. All right, so in your mind, you're probably thinking that's great and all, but we've identified a lot of stuff that that goes beyond just gravity acting. We've been talking in friction and all these other things. So why are you giving me tools that only work when gravity is the only thing acting on an object? Well, if forces other than gravity are doing work on the body, then the total work is not given by just work grav, not that alone, it's driven by something in addition to that. So there's some other work being done, and I'm going to call that work other. And that is what the total work is equal to. Right? So there's lots of other forces, and some of those forces can be doing work on our body. So if that box, if we were considering friction, then friction force would be doing negative work on our object. And so it would fit into our equation like that. Okay? So what does that mean? If we bring that all back in, that just means that the change in kinetic energy is plus work other is equal to K2 minus K1. So the total work is equal to the total change in kinetic energy. That's the work energy theorem. So now the total work is not just W grav, it's W grav plus W other, and so we have this equation here. So for potential energy, right? So for this basically equates to U grav 1, minus U grav 2. Then we have our other work, other, and that is equal to the total change in kinetic energy. Okay. So the expanded form, considering any other work being done on our body other than gravity, is this. K1 plus U grav 1 plus work from some other source is equal to K2 plus U grav 2. So the kinetic energy at moment 1 plus the potential energy at moment 1 plus what other work is also contributing is equal to the kinetic energy at moment 2 plus the potential energy at moment 2. And to write this out further, of course, we have 1/2 mv1 squared plus mgy1 plus, we'll leave this as it is because it can take many different forms, 1/2 mv2 squared plus mgy2. Okay. So this is an expanded form. It's a more full form. Notice that this form works for the problem that we did before. It works for the case where gravity is the only thing acting on the body because work other is just 0. So you can start with this more general one and just make work other 0, and it works. So you see that when gravity is the only thing working on the object, it's just a special case of this more general form. And we're going to expand it a little bit more as our lecture goes on too. All right. So another way to think about what this equation means, other than what I briefly kind of went through, bring this back into view for sure, is that the work done by all forces other than the gravitational work, or the gravitational force, equals the change in the total mechanical energy of the system, right? Because this is the total mechanical energy of the system. There's something different on one side than the other. And this work other can be said to be the change in mechanical energy for the system. So something else is coming into play to add to the mechanical energy at the beginning, or take away from the mechanical energy. In the beginning, there is one amount of mechanical energy, and if work other is negative, then this is just some amount of mechanical energy at moment 1 minus, let's say, some work like friction. It's working against the direction of motion, so the work would be negative. Well, then the work would be less. The total mechanical energy of the system moment 2 would be less, right? Or if it's plus work other, so somebody pushing it or something, then you have some greater total mechanical energy of the system. Maybe that helps, maybe it doesn't. Okay. So if work other is positive, E increases. If work other is negative, E decreases. If work other is 0, then the total mechanical energy of the system is constant. And we're back to our earlier equation, like I had said. So let's do another example that involves some work, some other work. So this is going to be our example here. We want to slide a 12 kilogram crate up a 2.5 meter long ramp inclined at 30 degrees. A worker, ignoring friction, calculates that he can do this by giving it an initial speed of 5 meters per second at the bottom and letting it go. Here's the picture of what's going on. He's trying to shove this box up the ramp. But friction is not negligible. The crate slides only 1.6 meters up the ramp, stops, and slides back down. So, for A, we want to find the magnitude of the friction force acting on the crate, assuming that it is constant. And B, how fast is the crate moving when it reaches the bottom of the ramp? So before you dive into this, consider doing this problem, consider what it would be like doing this problem with just Newton's tools and our dynamics equations and such. It can be done. It's just incredibly difficult. It's a more complex scenario than we've seen before. So we have this like full kind of motion that we're considering. And so we've identified point 1, point 2 in the boxes up top, and then point 3. You know? It's kind of a complex system. But if we do an energy analysis, it might end up a little bit easier than you think. So the friction force does work on the crate as it slides. The box starts at point 1 at rest, then slides up to point 2, and then slides back down to point 3. Notice the fact that the ramp is 2.5 meters is irrelevant, right? It doesn't matter how long the ramp is. It may as well be an infinite ramp. It starts at point 1 with 100% kinetic energy and 0% potential energy, since we're defining y equals 0 at this point here, and thus u-grav equals 0 at this point here, at point 1. And kinetic energy decreases and potential energy increases as it slides up to point 2. And when it reaches point 2, the system is 100% potential energy and 0% kinetic energy. It has no motion, and it has some potential energy because of its position off of the ground. It then slides back down, and potential energy is traded for kinetic energy on its way down. At point 3, the system is again at 100% kinetic energy and 0% potential energy. But we have to be careful. Friction does negative work on the box on its way up as well as its way down. So work other is negative, and the total mechanical energy of the system goes down through this process. So its final speed when it reaches point 3 will be less than what it initially had. If we were not talking about friction, whatever its initial speed, as it headed off in this direction, it came back, it would be the same. But since we are including friction, it's scrubbing off some speed, we're losing some mechanical energy through this process, and the speed, as it gets to the bottom of the ramp again, is going to be less. You might be able to picture this if you picture a box sliding up and then sliding back down. So for part A, we are looking for, let's do this. Part A, we're looking for the force of friction. And specifically it's kinetic friction, but it's the only friction that we're talking about. So you might choose not to write that K. But the force of friction is equal to something. And the way that we know we're going to attack it is with energy analysis. K1 plus U grav 1 plus work other. Now we know that the friction force is doing negative work, but we're going to write plus work other, and then the work other will be negative, and so it'll end up negative in this equation, right? So equal to K2, the kinetic energy at point 2, plus the potential energy, gravitational potential energy specifically, at point 2. So let's cross out what's 0. Cross out our 0 terms. In the beginning, we have some initial speed, so K1 is not 0. But we're at ground level, so u-grav is 0. There's no potential energy on the ground if you've defined 0 to be the ground, because it's equal to mgy, and the y is 0. So the whole term is 0. Plus work other, that's going to be friction, not 0, is equal to K2, so point 2 up here. At the top, we said that there's 0% kinetic energy, because it's not moving, and it's 100% potential. So we've crossed out a couple 0 terms. Let's rewrite. So we have 1/2 mv1 squared, it's this term, plus work other is equal to mgy2. Yeah, okay. And what we know is that this work other is going to be our friction force times the distance. So you could write Fs, right? So before we were saying Fs, that's work, force through a distance. So our force is the friction force, and S is the distance, where S is this distance, S, there. Okay? And it's going to be negative, because the friction force is going to be negative. So let's go ahead and write this out. So we have negative Fs is equal to, I'll move that over here, mgy2 minus 1/2 mv1 squared. Yeah. And F then is equal to 1 over S, negative 1 over S, well, I'll just switch the terms, 1/2 mv1 squared minus mgy2. Switch the terms, got rid of that negative. Alright, and if you plug in the numbers, which I'll let you do, you should get that the force is equal to 35 newtons. Please check that on your own and make sure you know what we did here. Alright, what was part B? What did part B want to know? How fast is the crate moving when it reaches the bottom of the ramp? Put the problem back up here. How fast is the crate moving when it reaches the bottom of the ramp? Well, this is pretty easy, again, because all we have to do is do an energy analysis, yet again. Now we're solving for a different quantity. So, gotta get myself a new room first. Alright. So now we're solving for V3, because at the bottom of the ramp, after it's gone up and then back down, that's 0.3, as we labeled it on our picture. So for part B, we're looking for, let's go to this one. For B, V3 is equal to something. Right? So as the box slides back down from point 2 to point 3, friction does the same amount of work on it as it did on the way up. This is kind of a clever trick. You don't have to do it this way, but if you think about it, that is true. Work other on the way down is also going to be, the friction force. And it's the same distance, and it's working against it, so it's still going to be negative. And so the work other from point 1 to point 3 is going to be the work done from friction on the way up, and then the work friction done on the way down. And so if each of these is Fs, or negative Fs, then if you have two paths, two times that it's happening, then you just double that. You don't have to do it this way. You can analyze from point 2 to point 3 and do it the same kind of approach as before. But if you recognize these approaches, these little tricks, it might save you some time. So now we can do an energy analysis from point 1 to point 3, since we know the total work other through the whole journey is this. We want to find the final velocity, so we want to focus on K3. So K1 plus U grav 1 plus work other is equal to K3, because we're jumping from point 1 all the way to point 3, plus U grav 3. What can we cancel out? Certainly not work other. We already know what that is. There's no kinetic energy at the bottom at the start when it starts going. Or, oops, there is kinetic energy because we shove it off, but there's no potential energy because it's at the ground. And at the bottom, it has kinetic energy, and there's no potential energy again. So what we're left with is K1, and I'll just skip straight to writing it out. So 1/2 mv1 squared plus work other is going to be equal to this. So I'll just stick it in there. So minus 2fs is equal to this term, 1/2 mv3 squared. And v3 is what we're solving for. So if you go ahead and you solve for v3, let's skip a couple steps here. It's going to be under a radical, we know. v1 squared minus 4fs over m. And if you plug in the numbers, I'll let you do that, you get that the speed at the bottom is 2.5 meters per second. All right. So just like I said, we could have also analyzed the energy from point 2 to point 3. It might have been simpler. We would have gotten, of course, the same result, but you can do that if you want to test yourself or just get a little more practice in. But it's nice to recognize and kind of think of the big picture in these problems. So before we end this section, I want to give you some problem-solving strategies for working problems using mechanical energy. And I'm going to go ahead and bring this on over to you guys and just read straight off of it. So, these are my notes. So, problem-solving strategies. Let's see. That about right? So first, we want to identify the relevant concepts. Decide whether the problem should be solved by energy methods, using F equals ma directly, or a combination of these. The energy approach is best when the problem involves varying forces or motion along a curved path, which is discussed later in this section. If the problem involves elapsed time, the energy approach is usually not the best choice because it doesn't involve time directly. Then we get back to our kinematic equations, where time is involved in some of those equations. So, you want to set up the problem. So you're first going to identify the initial and final states, positions and velocities of the bodies in question. Use subscript 1 for the initial state and subscript 2 for the final state, and draw sketches showing the states. You're going to define a coordinate system and choose the level at which y equals 0. Choose the positive y direction to be up, and if you have gravity involved, then gravity works down. Identify any forces that do work on each body and that cannot be described in terms of potential energy. So far, this means any force other than gravity. So we'll talk about springs and such in the future, and we will. Sketch a free body diagram for each body. List the known and unknown quantities, including the coordinates and velocities at each point. Identify the target variables, and then you execute it. So write expressions for the initial and final kinetic and potential energies, K1, K2, U grav 1, U grav 2, and if any other forces do work, then you have to include work other. So this is something that this textbook does to help you visualize it, but I haven't accentuated that at all, so just ignore that part as I accentuate it. So then you just solve your variables. And then, as always, check your answer to make sure it's reasonable in value and in units. All right, see you in the next video where we build further and further on this concept.